here we go. 1.1, preview of calculus. Ha, David, thank you so much.
Calculus is the mathematics of change velocities and accelerations. Calculus is also the mathematics of tangent lines,
Yes!
areas, volumes, arc length, centroids, curvatures, and much more.
Beautiful. All right. So I think it's the mathematics of change. And I think of it this way. All the pre-calc stuff that you've done before, and I'm not just saying like pre-calc, but I'm saying like geometry, algebra, all that good stuff. Then you have limits, and then you have real math called calculus. All right. I think it's the bridge with those limits. Limits kind of connects both of them together, and we're going to talk about concepts of those things. So a lot of the times we talked with things without calculus, and I'm going to talk about things that we're going to develop with calculus. So how did you do a slope of a line without calculus? How did you do it? Rise over run. Exactly. Okay? Change in y over change in x. y2 minus y1 over x2 minus x1, right? And so all of that was that. But now we're going to do slopes of a curve. Because that's what calculus is. It's curvatures. It's smooth, curves, nice. All right? But now we did secant lines. All right? We did those in pre-calc. What did we call those secant line things? We did it in our second lesson in pre-calc. An average rate of change. That's how we did it. We found an average rate of change. That's the slope of a secant line. But now we're going to find slopes of a tangent line. What does it mean to be a tangent line? It only touches once. All right, secant lines touch how many times, Cohen? Twice. Look at that. We're on a good. We're good. We're good. All right. So all those people know the average rate of change. All right, the average rate of change. So remember those problems that says like the train travels at 50 miles per hour. Did the train travel at 50 miles per hour the entire time? No. Those are silly. Those are silly problems to me. All right, because if the train traveled at 50 miles per hour from stop A to stop B, people are boarding the freaking train at 50 miles per hour, and they're exiting the train at 50 miles per hour. People don't do that unless they're in Mission Impossible 8. Then they might, but other than that, they don't. All right? All right. Oh, it was a good movie. Good movie. All right. All right. But we're actually going to talk about instantaneous rate of change. So does anybody have a car?
Me.
Awesome. What's that little thing that says like those numbers? Like what's that thing? A speedometer. What does that speedometer tell you? How fast you're going. But what kind of fast? Is it average?
No. Per hour.
No, it's actually what? It's exact, but it's just what? It's instantaneous. It's instantaneous rate of change. All right, that's what we're going to talk about. So we're also going to talk about heights of a curve, but we're only going to do maximum and minimum heights of curves. And then how do you find an area of a rectangle? Because we need this one today, actually. Length times width, or base times height, exactly. But in calculus, we're going to do area under a curve. All right, we don't know how to do that without the use of calculus. So this will be good for this year. All right, here we go. So let's talk about algebra slope. All right, so we know algebra slope is y2 minus y1 over x2 minus x1. This is a good nugget right now. All right, and so our slope of our secant line, is this formula right here, but it's the same thing as y2 minus y1 over x2 minus x1. Because delta x is the change in x. It's how far out we go from where we're actually trying to have a slope from. And so it's f of c plus delta x. It's just this fancy way to write y2. But delta x is how far out we go from our point of tangency. And then minus f of c over c plus delta x minus c. And this beautiful thing happens is our c's cancel. So how do we find the slope of a secant line? By just doing what? Algebra slope. We just substitute in, right? Okay, we just substitute in, finding our algebra slope. But we're going to get closer and closer to this point of tangency. And without calculus, we can't really do it. So we're just going to have to use some algebraic techniques and guess. All right, that's what we're going to do today. All right, and then later on throughout the year, I get to teach you the calculus to get the exact tangent line. All right. All right, so the first function we're going to deal with is x squared. So our f of x is just x squared. And what we're going to do is we're going to get closer and closer to the point 1.11. Exactly. We're going to get arbitrarily close to this point 1, 1. All right. And so all we're going to do is we're going to find our slopes with like 1.5 f of 1.5 and 1, 1. All right. We're going to keep getting closer and closer to 1. All right. And so this is the way we're going to set it up. We're going to find f of 1.5 minus f of 1 over 1.5 minus 1. So all we're doing is algebra slope. Okay? So what is 1.5 squared? What is 1.5 squared?
Shoot.
2.25, exactly. And then minus, what's f of 1? What's 1 squared? 1 over 1.5 minus 1 is 0.5, exactly. All right, so we're going to do the rest in our head. We got this. We're smart people. So now we have 2.25 minus 1, which is how much? 1.25. Dividing by 0.5 is really multiplying by 2. It's multiplying by 2. And so what do we get? What's the slope between 1.5 and 1? 2.5, exactly. So the slope of that secant line is 2.5. But right now, my delta x, going from 1 to 1.5, what's my delta x? How much am I changing? I'm changing 0.5. That's kind of a lot. So I want to get closer. And so we're going to get successively closer here. And so now we're going to have it at 1.1. And so now we're going to have f of 1.1 minus f of 1 over 1.1 minus 1. And so what is 1.1 squared now? What's 11 squared? Yeah, exactly. So now instead of 121, we're at 1.21 minus f of 1, which is 1 over 0.1. So now I have 1.21 minus 1, which is 0.21. Divided by 0.1 is really multiplying by 10. It's multiplying by 10. And so now we get what? 2.1. And so now we're going to get closer. So now we're going to get 1.01 now. All right, so now we're 100th away from my delta x. And so now I'd end up having f of 1.01 minus f of 1 over 1.01 minus 1. So this is a lovely little pattern. So 1.1 squared is 1.21. What's 1.01 squared? 1.0201. Exactly. Minus f of 1, which is 1 over 0.01. And so now 1.0201 minus 1 is really 0.0201. But then instead of dividing by 0.01, that's the same thing as multiplying by
100.
Look at you. Sheesh. And so now what do we get? 2.01. Now, I have not found the slope of my secant line of Q4. And Q4 happens to be a delta x of 0.001. But what do you think it's going to be? 2.
20. I think it's just 2.
It's not just 2.
5, 1.
2.001.
Oh, I thought we were estimating. Sorry.
Because if I did 1.001 squared, I would actually have 1.002001. All right, it's a lovely pattern when you actually square those things. But my slope is going to be 2.001. Now, if I get even closer to like the what is that, the 10,000ths? If I get even closer, what do you think it's going to go to? What do you think it's getting closer and closer to, Lane? 2, exactly. So the slope at 1, 1 is actually what? 2. Now, did we actually use calculus? No. Are we actually ever going to get to a slope of 2 without using calculus? No. But what's it going to get really, really close to?
2.
It's going to get really close to 2. All right? And so our second major concept is area under a curve. All right? Area under a curve. All right? So I have these rectangles kind of representing my area under these curves. All right? Which one do you think is better? Which one do you think happens to be like a better estimate of the area under the curve? The one with 4 rectangles or the 8 rectangles?
8.
Campbell?
I go 8.
8 rectangles. Why 8 rectangles, Campbell?
Because there's more. I don't know. Because it has more things there.
More money, more problems? Why is 8 more better?
Because you get a better approximation.
Better approximation. Okay, why?
Because if you multiply by 8 lengths times width, you're going to get like closer to the actual value of the area.
Closer to the curve? So what if I use
Closer to the
16
value.
rectangles?
You're going to
Even
be still
better.
closer.
That's better?
Yeah.
Sheesh.
It'll fill it in a lot better.
All right. Who's ever seen Rocky? Rocky Balboa.
Oh,
Rocky.
we actually made a new Rocky.
All right,
video,
it's
actually.
a great movie.
Using bowling.
Yo, Adrian! There's a point in the movie that says Adrian fills in his gaps. All right, that's the way I think of it. All right, it fills in its gaps better. You see how you have less gaps in that one with the 8 than you do with the 4. All right, and so I always think of Rocky when we do these area under the curves thing. That's just the way I think. All right, so let's kind of talk about some stuff here. So on this one, it's called an inscribed rectangle. All right, and inscribed means kind of underneath. I would write that down. All right, inscribed means it's underneath the curve. It doesn't necessarily mean it's left or right, and I'm going to talk about that, but it means it's underneath. A lot of the times, we're going to call this a left hand, or a left Riemann. It's actually named after George Friedrich Bernhard. He had 3 names, and then Riemann. But, Bernhard. Yeah. I'll give you kid names. That's good. All right. But a lot of the times, we call this one from the left. Do you see how the left part of the rectangle touches? That's why it's called from the left. But inscribed means it's underneath. And I don't want you to think that every left is an underneath, because if it's a decreasing function, then a left hand would actually do what? Go over it. And that over thing is called a circumscribed. All right? We're not going Old Testament. All right? It's circumscribed. Okay?
I get it.
And so circumscribed is actually going to be what?
Over.
Over. All right, over. But a lot of the times we'll call this kind of example a right. Okay? Because what part of the rectangle does it touch?
The right.
It touches the right. Okay? That's more likely of how we're going to be exposed to it when we get to chapter 4. All right? But circumscribed means what? Over. Exactly. And I don't want you to think of it because, like, if you have a decreasing function, a right hand would actually be what?
Inscribed.
An inscribed. Exactly. All right. So there's some new terminology for you right there. All right. Let's keep moving. So again, we're going to deal with the function of x squared. All right. I got to set this one up. So my function is x squared again. We're just going to go simple. And I'm going to go from x equals 0. And I'm going to have my bounded area from x equals 0 to x equals 1. Now, how many partitions, how many rectangles did this one have? I want you to look at the picture on this one. How many rectangles did it have? Most people get this one wrong.
Well,
How many do you see,
I
Emil?
see 4, but I'm gonna guess it keeps getting smaller.
Okay, there you see 4. I see 4 as well. However, that's not the answer. How many rectangles are there? What? There's 5. There's 5. There's 5 rectangles. There are actually 5 partitions. You just don't see this one. Why don't you see that one right there, that little booger? Why don't you see it? Because what's the height? The height's 0. All right? And so this actually has 5 rectangles.
So you always add 1?
No.
Okay, sorry.
All right? All right. So this one actually has 5 partitions. So I want you to write this one out, and we'll do a lot of it in chapter 4. We're going to write b minus a over n. And this b is actually where you go. The a is where you start. And the n is the number of partitions, or the number of rectangles. Even though you only see how many rectangles here? 4, because the 5th one is actually a height of 0. All right? And so this is actually going to give me my width. This is actually going to give me my width of each rectangle. All right? So, my b is actually what?
Where you go? Well,
1 minus, where did I start? 0 over how many partitions? 5. And so my width is what? 1/5. Or, if you go decimal style, what? 0.2. All right?
What's the decimal stuff around here?
We're going to approximate using these inscribed, or, is this a left or a right, by the way?
It's a right or a left.
This is a left.
It's a left.
This is a left, because which side touches the left? That's why it's called a left. All right? So, my width is 0.2. How do we find the area of a rectangle, by the way? Length times width. All right? So I just need to find the heights of all of them. All right. And so I'm going to have 0.2 times f of 0. And that's going to be the height right there at 0. And then I need to go a width away. And so now I'd have 0.2 times f of 0.2. Because that one's at 0.2 right there. And then I would have 0.2 times f of 0.4, exactly. Plus 0.2 is my width again, and then I need to get a height at f of 0.6. And then 0.2 times f of 0.8. Do I do another one? No. Because if I did another one, it would actually do it all the way to 1.2. I don't want that one because how many rectangles do I want? I want 5. All right?
How do you know when to do 5 and when to...
So on this one, I like to factor out my 0.2. I like to factor out my 0.2. All right? So now let's kind of just like go with it. So what's f of 0? So evaluate 0 squared. What do we get?
0.
0. Plus 0.2 squared. What do we get? 0.04. Thank you. Plus, what's 0.4 squared? 0.16.
Close.
And then, what's 0.6 squared? 0.36. And then plus 0.8, 0.64. All right. Now let's do some math. 0.36 plus 0.64?
100.
1. All right. And then 0.04 plus 0.16 is 0.2. So I got 1.2 times 0.2. So 1.2 divided by 5, basically.
0.24.
0.24.
I knew that. I did that in my head actually.
So we got 0.24 is the area approximated under that curve. Now, is that area over or an underestimate?
Under.
It's an underestimate. Why is it an under, Luke?
It's inscribed.
It's inscribed, and so there's some gaps. There's some gaps, isn't there? All right, so now let's do circumscribed. This case is going to be a what? It's an overestimate. Is this one going from the left or the right? This is going from the right. Why is it from the right? Because the right corner touches. All right? All right, so my width is still going to be the same because my b minus a is the same, my number of partitions is the same. So what's my width each time again? 0.2. So I'm going to factor that little booger out still. And so now I got 0.2 out there. Now back in 2016 I got changed. I actually used to go from the left even though I'd go from the right, which is crazy. And then like the people, like my students were like, no, go from the right. And so I've done that ever since. And so now I'm going to find f of what? 1. And so we're going to kind of go backwards, all right? And so some textbooks, actually most textbooks don't do this way. Actually, all of them
Wait, so now we're
don't
not
do
gonna
this way.
find f of 0 though?
Then we're not going to find f of 0. Good job. All right? And so what would be my next one? F of what? Not 8, but 0.8. All right? Because my width is still what? 0.2 away. All right? So I'm still going from 0.2 away. And then my f of 0.6. Good. And then f of 0.4. And then f of 0.2. Now, do I actually get to 0?
No, we can't.
I don't do f of 0 because then how many partitions would I actually have? I'd have 6. I don't need 6 rectangles. It wouldn't change the game on this one, but or my answer, I should say, but it would change how I'd do it. All right. So let's do some math. So 0.2 times, what is f of 1? 1. Plus, what's 0.8 squared? 0.64. I feel like we've done this before. And then 0.36. And then,
0.16.
and then,
0.04.
and then,
And then.
that's it. All right.
And then. Wait, what is that?
And so then, what do we get? So all of that was 1.2 before. So now we're going to add what to it? Now we have 2.2. Exactly. So 2.2 divided by 5 is?
Say my name.
0.44. Good. All right. So we got 0.44. Is that an over or an under approximation of the area under the curve? An over. Now, I know we're not really taking this step yet, but I'm going to right now because I'm curious. how would we get better approximations?
Average it more.
Average it. I love that.
More rectangles.
So, more rectangles and average it. That's exactly right. All right. So, what would be the average of 0.24 and 0.44? 0.34. Exactly. So, does anybody know the actual area under the curve from 0 to 1 of x squared? It's 1/3, which is 0.3 repeating. Now, is 0.34 pretty close to 0.3 repeating in my opinion?
I'm gonna check that out.
I think it's pretty good. All right. So, how would we actually get closer though? More rectangles. I bet you if we did 10 and we averaged them together, I bet you would get pretty daggone close to that 0.3 repeating. All right. And so that's what we'd do. So your little bit of homework is page 47, numbers 1 through 10.